So now exponential decay. Exponential decay is very similar to exponential growth. All right, a quantity. The difference is we're losing the same percentage over a given time period. All right, so a quantity decays exponentially when it decreases by a constant percentage over. The difference here is you're losing value. You're decreasing. Your money is losing. Your quantity is losing amount. Assume the quantity decays exponentially. We let r be the percentage as a decimal. This time, though, since we're losing, we're going to subtract. You take your 1 represents the initial value. R is how much you're losing from that initial value. That's what that R. And so when it's a loss, you take your percent and subtract. All right, subtract it. You subtract it because you're losing that percent. And so when you do exponential decay, the difference is the equation's set up very similar, but when it's decay, you take 1 minus the percent because that's the percent you're losing. When you're doing growth, it's 1 plus the percent because you gain that much. So it's the remaining amount, the future value, equals the initial amount. That's still the same, so Q naught still represents the initial amount, but the difference here is it's 1 minus the percent as a decimal, 1 minus R, raised to time, and again, the units must match. Right? If R is years, T needs to be years. If R is in days, T needs to be in days. If R is in hours, it needs to be in hours. All right, so those things need to match. Again, T is the number of periods for exponential decay. The base should always be 0 to 1, so make sure you're careful. It should never be negative, and it should always be less than 1. So some decimal between 0 and 1. Exponential decay tends to decrease fast and then slows down. And so the shape of the graph typically is you have this initial value here, and then it shoots down really fast, and then it tapers off because eventually you're getting, so it's just small amounts that it's decreasing slower and slower and slower. So that's what it means. So it comes down really fast and then it slows down. So it's not a line because it's got a curve to it. Alright, so suppose this is my example. Suppose the number of people visiting the library per year since 2000, so 2000 would be times 0, represented by the function 182,000 times 0.92 to the t. So you'll notice that it's 0.92. The base is between 1 and 0. It's bigger than 0 and smaller than 1. When that's the case, it's a decay because I'm losing percent. It means I took 1 and I subtracted it. Alright, so our initial value was 182,000. 2000 was our times 0. Now I guess we'll put that here. Initial value is 182,000. People visit the library. Right. It's a decay rate given as a rate. We know it's a rate because the inside would be 1 minus R. It came out to 0.92, right? That's less than 1. If it's bigger than 1, it's growth. If it's less than 1, it's decay. So I have to figure out, well, what is R? What did I subtract? What percent did I subtract here? And again, you could probably figure that out in your head, but if you're solving it, you would subtract 1, so you get negative R is negative 0.08, divide by my negative 1, and so my R is 0.08. That's not the answer. We want it as a percent. So remember, you take the 0.08 times our 100%, so it comes out to 8% is my R. Alright, so they're losing 8% every year. So 8% fewer people are going to the library. How many people visited the library in 2007? So remember, 2000 is my initial year. That's times 0. And so 2007 would be 7 years later, and so that would be T7. So you plug in 7 for our time. 7 years after the start, right? We started at 2000 with 182,000. We lost 8% every year, and so T represents the years after that initial starting value. So 7 is my years. So P is 182,000.92 raised to the 7. Comes out 101. Again, round to the whole person. Don't give me a fractional person. So by 2007, the number of people visiting the library dropped down to 101,528. Alright, stop there. I'm going to pick up the next examples in the next lesson.